For most of human history, if you wanted to build something strong, you cut down a tree. Wood raised our first villages, our first ships, our first cathedrals, and for 10,000 years, nothing seriously challenged it. Then the modern world showed up and broke the deal. A construction-grade tree still needs 25 to 75 years to grow tall enough and dense enough to become a beam, but the planet is not building on a 75-year clock anymore. It is building faster than at any point in recorded history, and forests simply cannot keep pace. So the industry turned to steel and concrete instead. And today, those two materials alone are responsible for well over 15% of all the carbon dioxide humanity releases every single year. Slow and green, or fast and filthy. That was the choice. For decades. Then, a team of researchers in Hong Kong took a plant that engineers had spent a century mocking as a peasant material, dissolved it down to its cellulose, crushed it back together under heat and pressure, and produced something that, pound for pound, is now stronger than industrial steel and titanium alloy. And it is already holding up a 7-story building in China. If stories like this catch your attention, stick around because this one gets stranger the deeper you go. To understand why this feels so sudden, you need to understand why nobody managed it sooner. The plant in question is bamboo, and on paper it has always looked absurd in the best possible way. It is the fastest growing plant on the planet, with some species capable of shooting up more than a meter in a single day. It reaches full structural maturity in 6 to 9 years instead of the decades a timber tree demands. It is technically a grass, so when you cut a stalk down, the root system underneath stays alive and simply sends up another one, no replanting required. Raw bamboo fiber, tested for pure tensile strength, already beats steel by a wide margin relative to its weight. People across Asia have known this instinctively for centuries, using it for scaffolding, footbridges, entire homes. But a raw bamboo stalk is also a structural nightmare. It is hollow, round, awkward to bolt together, prone to splitting along its length, and its strength varies wildly from one stalk to the next and even along the length of a single stalk. No building inspector can certify a beam that performs differently every time you cut a new one. So, for 100 years, the engineering world filed bamboo under huts and garden fences, not skyscrapers. The shift that changed everything did not come from growing a better bamboo plant. It came from refusing to build with the plant's natural shape at all. Researchers at City University of Hong Kong, led by material scientist Liu Yang, started with ordinary moso bamboo and asked a strange question. What if the weakness was never the fiber itself, but everything sitting around it? Bamboo is roughly 45% cellulose, the strongest structural component, mixed with hemicellulose and lignin, the weaker glue holding the plant together. So the team split bamboo stalks into thin strips and soaked them in a heated alkaline bath, a process that dissolves away most of the hemicellulose and lignin while leaving the cellulose network intact. What is left behind is a fragile, almost skeletal lattice, nearly pure cellulose. Then, instead of gluing that lattice back together with resin, they pressed it in heated metal molds under enormous force, squeezing out the internal air pockets and compacting the fiber down to roughly 30% of its original thickness. No formaldehyde, no toxic adhesive, just compressed cellulose, hydrogen bonded to itself. The result is a material commercialized under the name Super Bamboo, and the numbers coming out of testing are the kind that make materials engineers stop scrolling. It measures roughly 3 times stronger than ordinary bamboo. Its specific strength, meaning strength divided by weight, now exceeds that of industrial steel and even titanium alloy, and its stiffness runs above 5 times that of untreated bamboo. It picked up a gold medal at the Inventions Geneva Evaluation Days, one of the world's most competitive innovation showcases, and it holds patents in both the United States and Hong Kong. It is also water-resistant and fire-retardant straight out of the press, without a chemical coating layered on afterward. A startup spun out of the research, also called Super Bamboo, is now pitching the material for furniture, construction framing, and eventually automotive and aerospace parts, categories that used to be permanently off-limits to anything grown out of the ground. But a strong block sitting in a university lab is not the same thing as a strong block holding up a real building with real people walking through it. And this is where the story gets genuinely hard to dismiss. In Ninghai County, near Ningbo in eastern China, engineers from Zhejiang University, working with the University of Illinois Urbana-Champaign, designed and built what is now recognized as the world's first 7-story engineered bamboo building. The Ninghai Bamboo Tower stands 20.3 meters tall across 6 main floors and an attic, with roughly 800 square meters of floor space. The first two levels sit on concrete, but everything above that rises on glued laminated bamboo and cross-laminated bamboo timber panels, engineered under the same design logic as modern mass timber, but grown from a plant that regrows itself in under a decade. The structural team ran full seismic and wind load testing against existing timber design codes before a single panel went up, and the components were prefabricated off-site and assembled so efficiently that entire floors went up at a rate of 3 stories in 2 days. That speed is not a gimmick. It is the entire argument for the material in one sentence. Something that regrows almost as fast as it gets built. None of this is happening by accident, and it is not a niche research curiosity either. It is national policy. China currently holds close to a fifth of the entire planet's bamboo resources, spread across more than 7.5 million hectares of forest, and the government has built an industrial supply chain to match. In 2025, China's domestic bamboo industry crossed roughly 420 billion yuan in annual output, and Beijing's own targets project that figure climbing past 1 trillion yuan, something in the neighborhood of $150 billion, by 2035. There are more than 10,000 bamboo processing enterprises operating across the country right now, and close to 10 million people work in the sector in some capacity. On the climate side, the math is just as striking. A single hectare of managed Moso bamboo forest can pull down somewhere between 5 and 12 tons of carbon per year depending on management practices, outperforming comparable conifer plantations, and China's Moso bamboo alone is estimated to hold over 600 million tons of stored carbon nationwide. In 2008, China opened what it describes as the world's first bamboo carbon sequestration trading project, treating forest growth itself as a tradable climate asset years before most countries had a framework for that idea. That kind of institutional weight is exactly why the rest of the world is starting to move too. Engineered bamboo manufacturing clusters, once concentrated almost entirely inside China, are now appearing in the United States, India, Indonesia, Vietnam, and Singapore, with South American countries sitting on their own giant timber bamboo species beginning to treat it as a genuine export material rather than a garden plant. Still, it is worth being honest about where the limits sit. Even the newer glue-free version of engineered bamboo remains more expensive to produce than ordinary timber, because turning a hollow stalk into a dense structural panel takes far more manual processing than milling a log ever did. And cost comparisons published this year put laminated bamboo lumber at roughly double or triple the price per cubic meter of standard softwood glulam. Building codes, for good reason, move slowly, since every country that wants to build seriously with this material needs its own testing regime, its own certified inspectors, and its own legal paper trail before an architect can specify it for a hospital or a school. China can hand over the blueprints. Everyone else still has to do the slow, unglamorous work of writing their own rules around it. Even with those limits in view, look at what actually happened here. A plant the engineering world spent a century calling too weak and too unpredictable for real construction got dissolved down to its strongest component, pressed back together without a drop of toxic glue, and turned into something that beats steel on a strength-to-weight basis. And it is already carrying 7 floors of real weight in a real Chinese town. Wood took 30, 50, 70 years to regrow what we cut down. This regrows before a child finishes primary school. If a plant this ordinary was hiding a material this disruptive the entire time, it raises an uncomfortable question worth sitting with. What else have we already dismissed that we simply never bothered to test properly?